What's up, chemistry people? It is Mr. Boylan back for a new video, new unit, same amount of fun. In this video, we are going to explain how the rate of a reaction is measured by the amount of reactants converted to products per unit of time. Breaking it down as always. Number 1, we are going to describe 4 factors that influence the rate of a reaction. Numero dos. We're going to define average rate of a chemical reaction. Numero 3. Define instantaneous rate of a chemical reaction. And finally, numero 4. Explain how colorimetry and Beer's law can be used to determine the rate of a reaction. Alright, first thing I want to talk about in this vid are my good friends, the tortoise and the hare. Notice that throughout these presentations, they're going to be running across the top of your screen. And I think they do a great job of getting at what this unit is all about. If you haven't guessed it by now, / haven't read your screen, this unit is all about kinetics, which is the study of the rate or speed of chemical reactions. How fast, how slow a chemical reaction will occur. Now, I think there's a great illustration on your screen and in your notes that gets at the meat and potatoes of this idea. On one side of your screen, you've got a reaction with a fast rate. On the other side, you've got a reaction with a relatively slow rate. Notice that at time 0, for both reactions, we're starting with all reactant particles. But notice what happens as time progresses. As we proceed from time 15 to 30 to 45, the reaction with a fast rate very quickly converts all of its reactants into product. But our reaction with the slow rate doesn't do so as quickly. Take a moment, pause the video, stare at this image, stare at it in your notes, just stare at it. It won't be weird at all. Alright, and just a couple other quick things before we dive in. It's important to note that thermodynamics, which we just discussed, examines whether or not a reaction will occur. Whether reaction is thermodynamically favorable or unfavorable. But kinetics, which we're studying in this unit, is going to look at how fast a reaction will occur. And that's an important distinction to make, because we can have thermodynamically favorable reactions that happen so slowly that we can't even notice that a reaction is taking place. And 2, there is no way to predict a reaction rate in advance. Each reaction must be studied individually and determined experimentally. So great news for all you folks who like to do lab work. First, let's talk about 4 factors that can affect the rate of a chemical reaction. Number 1, increasing the surface area of a solid reactant can increase the rate by increasing the number of collisions between the reactant particles. Take a look at this thrilling image that's on your screen. On the one side, you've got a solid reactant in blue that's all stuck together, very small surface area. So the surrounding red reactant particles can only attack or react on that small outside surface area. But by crushing it up into smaller pieces, which is what you see on the other side of your screen, it enables the other red reactant to react with the solid blue component over a greater area and therefore react more quickly, increasing the rate. Less tortoise, more hare. Factor number 2, catalysts will increase the rate of a chemical reaction by lowering the activation energy. Now, how they do that we'll talk about a little later, but at this point, simply recognize that they function by lowering the activation energy. So as you look at this energy profile, notice that the uncatalyzed reaction has a much higher activation energy than the catalyzed reaction. And by lowering that activation energy, you make it possible for a greater number of reactant molecules to obtain that activation energy and therefore allow the reaction to proceed more quickly. Factor numero 3, increasing the temperature results in a faster reaction. As we'll learn, something called the rate constant is temperature dependent. And so if you raise the temperature, you're going to increase that rate constant, therefore increasing the rate of the reaction. All right, now let's take a look at this generalized reaction that occurs between element A and compound BC. I'm going to start us off at a very low temperature. Notice my particles are moving very slowly. Not a lot of effective collisions. Not a lot of product formation. Heat 'em up, speed 'em up. Boom! Check them out now. They're flying around like crazy. A lot more effective collisions. The formation of a lot more product. Heat 'em up, speed 'em up. Heat 'em up, speed 'em up, heat 'em up, speed 'em up. Factor number 4, increasing the concentrations of reactants, increasing the amount of reactants that collide with one another, thus increasing the rate of the reaction. Let's take a look at this thrilling reaction again. Very low concentrations of my reactants. Not a whole lot of collisions that occur between those two reactants. Therefore, the rate of this reaction is very slow. I haven't even formed any product yet. Boom! Notice what happens when we bump up the concentrations. Lots more collisions, much greater chance that we're going to have some reactant particles that are colliding with the correct orientation and correct amount of energy. Therefore, we're producing more product. All right, next thing to think about then is how are we going to quantitatively measure or define rate? One way to do that is by defining the average rate of a chemical reaction in terms of the change in concentrations of reactants or products over a change in time. Now, you can measure a rate as a decrease in a reactant concentration per unit time, or as an increase in the product concentration per unit time. And it's important to note then, when we talk about rates, our units, because of how we define them in terms of changes in concentration over changes in time, will always be written as molarity per unit time in some fashion. There's a few different ways you can do that. So take a moment and look at the different ways that we can express molarity per unit time. And importantly, as you look at the general reaction on your screen, to avoid ambiguity when we're describing rates of reaction in terms of different reactants or products, it's customary to divide each change in concentration by the appropriate coefficient that you see in the balanced chemical equation. So as you look at how we define rate in terms of reactant A, notice that it's divided by a coefficient of 1, or maybe you don't. As you look at reactant B, notice that it's divided by a coefficient of 3. Product C, divided by a coefficient of 2. And again, that sort of eliminates the ambiguity depending on how we define the reaction rate in terms of any of the reactants or products. It's also important to note that the concentration of a reactant decreases with time. So changes in concentration of your reactants are going to be negative. And because negative rates don't make a whole lot of sense, we throw a negative in front of our rate of reaction definition when we're doing it in terms of a reactant. So again, notice with this generalized reaction, for our reactants A and B, we've thrown a negative in front of there because our change in concentrations for those reactants are going to come out negative. And the concentration of a product increases with time, so change in concentration of your products is going to be positive. Boom. Notice no negative sign required here. Okay, now let's take a look at a concrete example, such as the synthesis of ammonia from its elements. Notice how we can define the rate of this reaction in terms of any of the reactants or products, and recognize again that those rates divided by their respective coefficients in the balanced chemical equation. We can define the rate of this reaction. So, if, for example, we were given the rate of production of ammonia to be 4.0 times 10 to the minus 3 molarity per second, we can determine the rate of consumption of nitrogen gas simply by dividing our rate of ammonia by 2. Boom. So notice that the rate of consumption of nitrogen gas is going to occur at half the rate of the production of our ammonia gas. Or, a little trickier, if we wanted to think about the rate of consumption, hydrogen gas, recognize that it's going to occur at 3/2 or 1.5 times as quickly as the rate of production of our ammonia gas. So again, if we know the rate of production of ammonia, all we need to do is essentially multiply that value by 3/2 to get the rate of consumption of hydrogen, which is 3/2 or 1.5 times faster than the rate of production of ammonia. Average rates. Boom! Now, most reactions will slow down as the reactants are consumed. There's less reactants banging into one another. As a result, the average rates that are given by the expressions that we just discussed lose their meaning when measured over longer periods of time. So let's take a look at a reaction between hydrogen gas and iodine gas to form hydrogen iodide. As you look at the initial 20 seconds of the reaction, notice that the concentration of our hydrogen iodide over that time period increases very rapidly. We have a very fast rate of production over this initial 20 seconds. However, if we look at a 20-second interval of time later in the reaction, say 80 seconds to 100 seconds, notice that the change in concentration of our HI is much lower, and therefore the rate of the reaction is occurring much more slowly. So although the average rate of a reaction is one important way to define the rate of a reaction, it's important to keep in mind that the actual rate changes continuously, being greatest at time zero. Again, notice initially our rate of change, or the change in concentration of our products or reactants over time, is greatest initially. Therefore, we're often to look at the instantaneous rate of a reaction, which is given by the slope of a tangent to the concentration versus time curve. And again, as you look at this image, you are given a couple of lines tangent to each of the curves to determine the slope, and therefore the instantaneous rate of change at that given time. Now, important to note that instantaneous rate at a given time of a reactant is equal to the negative of the slope tangent to the curve. So again, as we take a look at this reactant, we are going to get negative slopes of lines tangent to that curve, and therefore we're going to throw in a negative so that our rate value will come out positive. And instantaneous rates at a given time for a product are equal to the slope tangent to the curve. Again, because when you look at a product, slopes of the lines tangent to those curves are already going to be positive. Now, instantaneous rates taken near the beginning of a reaction, or time zero, is known as an initial rate. And initial rates are so important when it comes to the study of kinetics. And it's where we're going to focus a lot of our attention when we look at the rates of a given reaction. Now, if you have studied calculus, you will know that these tangent slopes are derivatives whose values can vary at each point on the curve, also known as the first derivative of a function. Now, if you're starting to panic, don't. There's no calculus on the AP exam, and it's not required to be successful in the course. However, if you're a calculus boss, go for it. You know you want to. Okay, and then lastly for this video, you might be wondering to yourself, wait a minute. If we are only able to determine the rates of a chemical reaction experimentally, how am I going to measure the concentration or the changes in concentration as the reaction proceeds? Answer: colorimetry. Not to be confused with calorimetry, which we discussed in our thermochem unit. We'll then use Beer's law to determine concentrations of solution as a reaction proceeds. And it's important to recognize that when you're doing this with gases, you can also measure the partial pressures of the reactants instead of concentrations to relate it to the reaction rate. Keep in mind, we can always use the ideal gas law, PIVNER, to determine molar concentrations. So let's imagine that we know Beer's law, or we check it out on our formula chart, and that we are a cuvette inside of a colorimeter, which is measuring the absorbance values. You could imagine how we might be able to do some really fun labs in which the color fades as the reaction proceeds. Or in which the color gets deeper as the reaction proceeds, therefore changing the absorbance. And if you know the absorbance and Beer's law, you can solve for concentration. So get ready for some thrilling times in the lab, although don't get too absorbed, and have a fantastic day.